Jason Dittman was working through transit data from the MERTH telescope, TNGEZ, a set of small robotic telescopes in Arizona and Chile designed to search for rocky planets around nearby red dwarf stars. He had been doing this kind of work for years. The process is painstaking. You monitor thousands of stars. You look for tiny, regular dips in brightness moments when a planet crosses in front of its star and blocks a fraction of the starlight reaching Earth. Most dips are noise. Some are false positives. A small number survive every filter and become confirmed planets. On one particular night, the data showed a dip, a rocky planet, 1.7, 3 times the radius of Earth, 5.6 times its mass, orbiting a red dwarf star every 24.7 days, sitting squarely in the zone where liquid water could exist on its surface. Dittman published the discovery in Nature in 2017. His own words at the time captured what the field was feeling. "This is the most exciting exoplanet I've seen in the past decade. We could hardly hope for a better target to perform one of the biggest quests in science, searching for evidence of life beyond Earth." Then the field ran into a wall. Not with LHS 1140b specifically. With the entire class of planets, it belonged to rocky worlds in the habitable zones of red dwarf stars. One after another, telescopes trained on these candidates found the same thing. No atmosphere. Bare rock. The violent radiation environment of a red dwarf star had stripped them clean. Researchers began to wonder, out loud and in published papers, whether the question had already been answered. Whether any rocky planet orbiting this type of star could hold onto its air at all. Dittman himself said it. We were getting to the point in the field where maybe all of these planets don't have atmospheres, and we need to look at ones around sun-like stars instead. Then a graduate student at Harvard ran the numbers on LHS 1140b, and what he found changed the question entirely. Before we go further, this channel covers what is actually happening in space right now. Subscribe 1 second. You will not want to miss what is coming next. To understand why LHS 1140b matters and why what was just published in Science on July 17, 2026 is a genuine milestone rather than an incremental finding, you need to understand one fact about the universe that most people have never been told. Red dwarf stars make up approximately 73% of all stars in the Milky Way. Not a minority, not a significant fraction, nearly 3/4 of every star in this galaxy is a red dwarf. They are small, cool, and dim, none of them visible to the naked eye from Earth, despite being the most abundant stellar type in existence. They burn their hydrogen so slowly that they do not age the way stars like our sun do. While the sun has a lifespan of roughly 10 billion years, a red dwarf can burn for trillions, far longer than the current age of the universe. Which means the vast majority of opportunities for rocky, habitable zone planets to exist in the Milky Way are concentrated around exactly this type of star. If rocky planets around red dwarfs cannot hold atmospheres, the implications ripple through the entire search for life, because you have just removed the most common type of stellar system from contention. The habitable zone of a red dwarf is small and close in, which makes it easier to detect transiting planets, easier to measure their properties, easier to study their atmospheres. Many of the most exciting nearby planetary systems, TRAPPIST-1, Proxima Centauri, and now LHS 1140 orbit red dwarfs. And the results from JWST on the inner TRAPPIST-1 planets had been discouraging. TRAPPIST-1b and TRAPPIST-1c both appeared to be bare rocks. Intense radiation from the star had stripped their atmospheres during the star's active early phase. The pattern was consolidating into a rule. LHS 1140b just broke the rule. The discovery did not come from a large institution with a billion-dollar instrument pointed at the right planet at the right time. It came from a doctoral student following a mathematical prediction. Collin Cherubim was a PhD student in Earth and Planetary Sciences at Harvard, working in the lab of Professor Robin Wordsworth, and jointly advised by Professor David Charbonneau, who heads Harvard's Department of Astronomy. During his doctoral research, Cherubim built a computational model of how planetary atmospheres evolve over long timescales around red dwarf stars. The model tracked how lighter elements, hydrogen and helium, behave when a planet is subjected to sustained stellar radiation. Hydrogen, being lightest, is stripped first. It escapes into space over millions of years. Helium, slightly heavier, is stripped more slowly. But on certain planets at specific combinations of mass, radius, temperature, and orbital distance, a window exists where the planet loses its hydrogen but retains helium. The result is a world with a helium-dominated upper atmosphere, sitting above whatever denser gases exist below. Cherubim applied this model to every known exoplanet, with measured mass, radius, and temperature. he built a ranked list. LHS 1140b appeared near the top. The model predicted it would have a detectable helium outflow, helium actively escaping from the upper atmosphere into space, producing a specific signal at 10,833 angstroms in the near-infrared spectrum. His advisor, Charbonneau's initial reaction was skepticism. His words recalled later, "My reaction was, that's crazy, because there's nothing like that in the solar system that's just the product of some mathematical calculation." He did not tell Cherubim not to pursue it, he told him to go find out. Cherubim went to get telescope time. The instrument he needed was the WINED spectrograph, the warm infrared Echelle spectrograph, to realize extreme dispersion recently installed on the Magellan Clay telescope at Las Campanas Observatory in Chile. A 6.5-meter telescope in the Atacama, one of the driest places on Earth. WINED had been designed to work in exactly the near-infrared window where helium's escape signature lives. Cherubim applied for observing time. He got it. On the night of the 23rd of September 2024, something rare happened. Both LHS 1140b and its companion planet LHS 1140c were due to transit their star during the same observing window, separated by only 39 minutes. A double transit event, a single continuous session of 6.5 hours that would let Cherubim measure both planets under identical conditions on the same night with the same instrument. His team collected 70 spectra across the session, 35 outside transit, 12 during LHS 1140c's crossing, and 23 during LHS 1140b's crossing. They processed the data using the WINED automatic reduction pipeline and looked for excess absorption at 10,833 angstroms, the precise wavelength where stellar X-ray and ultraviolet radiation excites helium atoms into a metastable quantum state, causing them to absorb starlight in a measurable way. LHS 1140c, nothing. The smaller, more irradiated planet produced no helium signal whatsoever. It is consistent with a bare rock. No atmosphere. LHS 1140b, a clear signal. Statistically robust. Helium absorption during transit, absent outside transit. Exactly where Cherubim's model had predicted it would be. At exactly the wavelength his model had predicted. Charbonneau's response when he saw the results. Collin analyzed the planets we knew about and predicted that this one would have a helium atmosphere. Then he organized telescope time, got the data, and the detection was statistically rock solid. Cherubim's own words on the moment he understood his prediction had worked. "I was just following the numbers. My model predicted escaping helium and a lot of it." The paper was submitted to Science. It published on the 17th of July 2026. Now here is what the helium signal actually tells us and what it does not, because the distinction matters and the coverage has not always been precise about it. What the signal confirms, LHS 1140b has a real persistent atmosphere. The planet is not a bare rock. It has retained atmospheric material for more than 3 billion years, the estimated age of its host star. The rate at which helium is currently escaping, modeled against the star's radiation output over that time frame, is inconsistent with a bare rock that sometimes burps up some gas. The escape rate implies a reservoir. Something below is continuously supplying helium to the upper atmosphere, which in turn loses it slowly to space. That supply implies a complex, layered atmosphere, not a trace exhalation. What the signal does not confirm, the composition of what is below the helium layer, the WINED spectrograph, is sensitive to the upper atmosphere. The denser, lower atmosphere, where the gases that matter for habitability live, is shielded from this specific observation. Nitrogen, oxygen, carbon dioxide, water vapor, none of them are detected or ruled out by this measurement. Cherubim's own climate models predict that carbon dioxide is the second most abundant gas in LHS 1140b's atmosphere, with carbon monoxide also present and small amounts of molecular oxygen. But those are model outputs, not measured. The measurements that test those predictions require a different instrument. They require the James Webb Space Telescope. LHS 1140b is already a selected target under the Rocky Worlds Director's Discretionary Time Program, a joint initiative between JWST and the Hubble Space Telescope dedicated specifically to searching for atmospheres on rocky exoplanets orbiting dwarf stars. The helium detection published in July 2026 does not conclude that investigation. It opens it. Jason Dittman, who discovered LHS 1140b in 2016 and is a co-author of the Cherubim paper, put the next question precisely. Because there's helium there, And because the helium is escaping, the question is LHS 1140b a bare rock with no atmosphere that sometimes burps up some gas that then immediately escapes? Or is there a steady state atmosphere there that will leak out stuff like the Earth does from time to time? JWST data over the next 4 to 5 years will look for water, and if there's water in the atmosphere, then it's probably a stable atmosphere that will persist. Water, carbon dioxide, methane, molecular oxygen. These are the gases that JWST's near-spec and nearest instruments will search for in LHS 1140b's transmission spectrum over the coming years. Each one would add a layer to the picture. Water vapor would suggest liquid water is possible. Molecular oxygen alongside methane would be a potential biosignature because the two gases destroy each other chemically and cannot coexist in equilibrium without some process continuously producing them. On Earth, that process is biology. Nobody is saying LHS 1140b has life. Cherubim said it explicitly. I'm not claiming this planet has life. Dr. Joe Barstow of the Open University was equally direct. What it does tell us is that rocky planets in close orbits around red dwarf stars can retain an atmosphere. The next step in evaluating the habitability of LHS 1140b is to learn what its atmosphere is made of, and for that we need more observation. The planet is not confirmed habitable. It is confirmed to have air. After years of bare rocks, that matters more than any single subsequent finding will. There is a detail in the data that the headlines largely skipped over. Cherubim's team detected helium in the 2024 observations. They also looked in 2025. In 2025, the helium signal was absent. The paper interprets this as time-variable atmospheric escape. The rate of helium leaking from the planet fluctuates with the star's X-ray and ultraviolet output, which itself varies over time. When the star is more active, more helium is driven into the metastable excited state that produces the absorption signal. When the star is quieter, the signal drops below detectable thresholds. This is consistent with what has been observed on hot gas giant exoplanets, where helium escape has been measured to vary with stellar activity cycles. The variability is not a problem for the interpretation. A planet with no atmosphere at all would not produce a detectable helium signal under any condition. The 2024 detection, combined with the 2025 non-detection, is consistent with a real atmosphere whose escape rate responds to its star's behavior exactly what atmospheric physics predicts. Cherubim is now leading an 18-month XMM Newton X-ray telescope survey to monitor LHS 1140's radiation output across a full stellar activity cycle to understand exactly how the star's behavior drives the escape rate variations. This is not tidying up loose ends. This is the field doing what it is supposed to do, following an unexpected result into the questions it generates. Here is what this discovery actually changes at the level above the specific planet. The field of rocky exoplanet habitability spent the last several years accumulating negative results. TRAPPIST 1b, bare rock. TRAPPIST 1c, bare rock. Multiple other targets studied by JWST returned flat transmission spectra, no atmospheric features, consistent with no atmosphere. The pessimistic interpretation was building momentum. Maybe the assumption that rocky habitable zone planets around red dwarfs could hold air was simply wrong. Maybe the radiation environment was always too severe. Maybe the search should redirect towards sun-like stars, where the habitable zones are further out and the stellar activity is lower. LHS 1140b resets that calculation. Not because it proves all red dwarf planets have atmospheres. It does not. TRAPPIST 1b and TRAPPIST 1c still appear to be bare rocks. But LHS 1140b shows that the outcome is not predetermined, that the factors governing whether a planet keeps its atmosphere are specific enough that some worlds around red dwarfs win the battle and some lose it. The question shifts from, can these planets have atmospheres, to which ones can and why. Robin Wordsworth, Cherubim's advisor and professor of environmental science and engineering at Harvard, framed the historical arc precisely. 20 years ago, we wondered whether other terrestrial-type planets even existed. Then we learned they're common, and found some in the habitable zone. The next question was whether any of them had managed to keep an atmosphere. Now we know at least one has. That progression, existence, then location, then atmosphere, is the roadmap for finding life. Each step took a decade. LHS 1140b just completed step 3. The next step is composition, and the step after that is biosignatures. The instrument doing the searching over the next 5 years is JWST, already operational, already pointed at this system as part of the Rocky Worlds program, already scheduled for follow-up observations. Cherubim himself now at the University of Chicago, is not finished with this planet. He has applied for additional ground-based time on a more sensitive Chilean instrument. Multiple independent teams are preparing their own observation. Everybody who can see it, in his words, is going to be training their eyes on it. 48 light years away, a rocky planet is holding on to its air against a star that has been trying to strip it for more than 3 billion years. We just found out it is winning. Next, a spent SpaceX Falcon 9 rocket has been drifting through space since January 2025. On August 5, it hits the moon at 5,400 miles per hour. Scientists at NASA, Los Alamos, and UT Austin have published papers predicting what happens. A crater, a debris plume reaching 75 kilometers high, an ejector spreading 1,000 kilometers across the lunar surface, far enough to threaten future Artemis moon base infrastructure. Nobody asked for this experiment, but it is happening anyway. And researchers are calling on every telescope on Earth to watch. Subscribe, that one is next.